Hello, my name is Bob D. Hilster and I am your particle model guru. This is the third video in a series of several videos on light. I've done one on reflection. I did one last time on dispersion, but that kind of got out of sequence. So I'm back to refraction, and this time I'm going to look at the rectangular and triangular prism. Now, last time, the last two times I asked this question, how many reflections, refractions, and dispersions do you see in this picture and where? And I got several no answers the first time, but the second time I presented it, David, my son, answered yes. He said there are 8, and that was my answer. There are 8 reflections, 8 refractions, and 8 dispersions. Then I asked an open question. What causes the light to reflect on the inside of the prism? Interesting question. David answered again, and he answers that there is a thin coat of water molecules. Well, that seems strange. No one would suspect that when you're looking at a prism and holding it that there's water there, but let's see what can be found out here. Found an article by a man who calls himself Glassman, who he actually does coating of glass, various coatings, and he apparently has studied what can be found around the surface of glass. This is his drawing. Air at the up top here. There's some absorbents here. Organic molecules can be there on the water, and then there's the water film. Now that's he's just saying that he isn't working with light and inside reflection. For him to show this, he must have some reason to understand that that's there, such that he can clean the glass before he coats it. The interesting part is about the inside reflection is that you must have something here that's like the outside. There must be something on the inside to cause the reflection. For example, if you take away all this stuff and just have pure glass somehow and none of this other stuff at all and no water, you would expect the light on the inside to come to the edge, refract, but not reflect, just go through. There's nothing to do that. So there is something at the edge that causes reflection, and there has to be a similar surface in the inside that causes reflection. What is that? And I don't know the answer, but this was an interesting possibility. So what I'm going to do today is try to predict the G2 force around the rectangular and triangular prism. I am predicting that because this is narrow and this is long, that the narrow side will have a smaller force than the long side. And on the triangle, the force in the middle here, where its longest, should be stronger and weaker. A simple prediction. I'm going to say, well, I wonder if I'm right on my prediction. So, finding the direction and magnitude. That's what I was trying to do, direction and magnitude of the force. To do this, I performed some simple experiments with both prisms and measured the angle of deflection. Now, that's a different word. This is not the angle of refraction or reflection. This is deflection. The angle of deflection is equal to 45 degrees minus the angle of refraction. And I brought a picture of this to show you. Hope you can see this. I have light coming in at 45 degrees. It gets refracted here and refracted there. And if you continue, the refracted angle is right here between the red line and the normal. and I extended that with the blue, and it comes out over here, and I'm calling this the angle of deflection, where this is the angle of refraction. This is the angle of incidence. And the reason I want to do this one is because this force vector, which I have in green, has a component that is pushing in perpendicular to the flow of light, causing that to turn. And it's this force, and this force makes it turn this much. So I'm going to go through and measure each one in various positions and see what I get. Okay, so I'm going to start with a triangle, and there's the answer, but I'm going to show you a picture. I'm going to change the video here and go to me only, and then I'm going to show you my actual paperwork on the prism. I got the prism in 3 different positions. Between 70 and 80 degrees at the top, there are 3 lines not parallel. Those 3 lines are the actual light lines that hit each of the 3 prisms, and each one comes down to its respective prism and happens to hit the line at 60 degree. Each one hits the 60-degree line. I put the prism in 3 different positions, always having the light coming in the same way, and I get that answer, 15 degrees. Did that 3 times on the triangular prism, and this is just again another drawing of the same thing. Whoops, let me go back here. This is a drawing of the same thing. And it shows the refraction here and then the refraction there, and I extended the angle of refraction out to here, but I'm measuring the angle of deflection in order to measure the strength of the force. 15 degrees is the answer I got. What have I got here? Have I got 2 triangles? No. Hit the right button, Robert. So I also did it on the rectangular, and I came in on the long side. Did the same thing in this case, because the light doesn't bend this way, it bends this direction. The light ended up over in this area. But when I extended this line, I marked on the paper, I marked this line, a point here and somewhere here, to draw a line to a point there. And it ends up on the 60-degree line. Again, for the rectangular prism, 15 degrees. I did slide this back and forth, and I don't have a picture of a like I had with the triangle, but it ends up being a 15-degree angle of deflection. And then finally I did it for the short side. This is much more complicated. In fact, this drawing is based on not a, I had to actually do a calculation to get this point, because it has an internal reflection and the line ended up here, so I marked here and I marked here and drew a straight line to the top of the prism. I had this point, I have this point, but I don't have this point. I have to kind of guess, look at the side of where the light's coming out and back in, and try to guess where that is. Decided that wasn't so easy to do, so what I did was I measured this length, and you may not see it too clearly, but the one I had measured this is a 1-inch dimension, and this came out 0.6 inches on this side, and this is 0.5 inches down here. And the fact that the angle of incidence and the angle of reflection is supposed to be equal, these 2 angles at this point have to be equal. I have congruent triangles, and I can solve the ratio of the 2 triangles to get this distance. So you can say that this line is to this line as this line is to that line. And then you could also say that the total is like 1.9 inches. It isn't quite 2. It was 1.9. And so I did the calculation, then I marked the point, and then I did the angle, and sure enough, it came out close to 15. I marked 15 here like it came out perfectly. It wasn't exact, but the way I'm doing this, not so exact. So all of them had the same index of refraction. So what about my predictions? Well, I haven't shown you, but whether I do the light from the left or the right, the angles are the same. So the direction of the force still remains perpendicular, but the strength of the force generated by a prism is constant. It's the same force here, the same force here, and the same force here, if my measurements are correct. Same thing with this one. All of these are the same because I slid this pyramid back and forth and I got the same angle. It refracts here, here, and here, all the same. Does the understanding of how the G2 net force is generated by the object is key to the model. It's the force that pushes the light. But apparently the edge is the primary function of this, not the distance, at least in the measurements. Now, I have to say that with the particle model and the G2 gravity, this net force of gravity that's pushing the light, I still would expect something like this. But apparently the edge is dominating this function. If I had the equipment and the accuracy to do anything better, I would hope to maybe prove this ultimately. But what I did here in a very simple way indicates that all of these are the same. So here's a simple analysis. The index of refraction for the two prisms. The sine of 45 relative, this is using Snell's law because that's how they develop the index of refraction. The sine of the angle of incidence, which is 45, is in proportion to the angle of deflection, which is 45 minus 15, gives me 1.41. And on scales that you look at, this is quite low, probably in the acrylic range, and of course it's red. I used red light. And so that has an impact on what that actual number is, but that's what you would get. And of course, I've already said, although I did not show the results, it's clear that the G2 net force is perpendicular to the edge, while the force at the corners, it's difficult to do any testing at the corner, so I leave that open. And it appears that the path length is not a significant part of the refraction. The primary cause is the composition of the prism at the edge, and as you've seen earlier, this gentleman who published a paper indicates sometimes these edges are quite messy. Okay, until more information is available to me, water seems to be the main cause of the inside reflection. It's you can take a prism, wash it, dry it, heat it up, but because water is easily attracted to glass, how do you get it to not have water? Because water being a solvent and the G2 force is going to push those water molecules against the glass. This does not explain the dispersion. I hope to go on back to that. When I first suggested there could be a second force of gravity that causes refractions in a prism, I did that in a video called Two Gravities. I knew that the full understanding of how the G2 particles interact with the prism was going to be difficult, just by looking at it. But over the time, if you go through all of the videos where I consistently use the G2 force to explain things, it's not only refraction. See, what I'm alluding to here is that now I generated the second gravity using a triangular prism, And then now I'm using the triangular prism to show what the G2 gravity force is, kind of circular logic, but I've applied this to many other cases. And it works very well. The fact that this is hard to explain is unfortunate. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.